Let's look at the dispersion diagram that comes out of this. So looking for eigenfrequencies for this constant basic state solution that we just derived. Looking at our equation, this is the constant background state derivation. That's the relation coming out of the dispersion. You plot those for each n. So remember, we have the Hermite polynomial and dependence on n here. So this term is related to the Hermite polynomial this way. There are two conventions. I'm going to ignore this one because in this convention you actually get negative frequencies. In this convention you make the wave number have negative numbers when it is westward propagating waves and positive when it is propagating eastward. Then the frequency remains positive, and this diagram obviously looks much more intuitive than this, at least for me. So let's ignore that, and this is being done for constant basic flow with the mean depth of 400 meters. So this is a key figure that you should remember, at least become supremely familiar with it so you never get frazzled about it. It's showing period in days here and cycles per day over here, frequency, and this is the zonal wave number. So you have the family of equations that we discussed in the first podcast as an introduction. You have the equatorial Rossby waves here, which you can see change slope at some point for different meridional modes. Then for n equal to 0, you have this mixed Rossby gravity wave, which at low frequencies begins to approach the equatorial Rossby wave solution, and at high frequencies it begins to head towards a gravity wave parallel to the Kelvin wave, which we will look in some more detail, which is n equal to -1. So these are essentially non-dispersive waves. Well, they are non-dispersive waves, which means phase speed and group velocity are in the same direction, group speed. So that's a solution for Hermite polynomial n equals -1. And then you have these family of westward propagating inertial gravity waves and eastward propagating inertial gravity waves, and you can see that there is a huge frequency gap here, and the question is what kind of forcing is required to generate these versus these, and we'll see that mixed Rossby gravity waves and Kelvin waves have some special features which allows them to respond in this gap. And you can see that as you go to higher wave numbers or higher frequencies, these have basically linear slopes, constant slopes, so they become non-dispersive, right? And the equatorial Rossby waves have negative slope here, and then they become positive slope at higher frequencies. Their frequency range, of course, is down here, but we'll see that that depends very much on equivalent depth as well as the basic state. So the large wave number equatorial Rossby waves or small scale short waves tend to be eastward propagating. The slope is going to become positive, and the low frequency Rossby waves or large scale Rossby waves have negative slope, and they propagate westward. So as we said already in the introduction, Rossby waves have westward group velocity and westward phase velocity for these long waves and low frequency waves, and they will have eastward phase speed but westward group velocity for the short waves. This has some implications for how the energy and the forcing is radiated out, and we will see some of those things. So this is a beautiful diagram that you should remember very well. So these are basically eigenfrequencies of families of equatorial modes, So eastward and westward inertial gravity waves, equatorial Rossby waves, Kelvin wave, and mixed Rossby gravity mode. The modes are plotted as a function of frequency omega and longitudinal wave number Ka. So we keep switching between K and Ka because westward propagating waves, as we said, have latitudinal dependence. You can think of A as the local radius, which is corresponding to the radius, local circumference. A is the radius for various latitudinal modes. Background state is at rest in this diagram, which is also same as background state being constant. Depth of the fluid is set to 400 meters. Negative Ka represents waves with westward phase velocity, and positive K and eastward phase velocity. Dashed line joins the d omega dk equals 0, thus differentiating between eastward and westward group speed. So we'll see where that split happens between eastward and westward group speeds for various depths and background states. Let's forget about the alternative representation. So you can see here the 0 line is basically should be here, but it's missing. Okay, nevertheless, let's look at the ubiquitous nature of mixed Rossby gravity waves and Kelvin waves. The eigenfrequency depends on h bar, so you can draw that same dispersion diagram for different depths going from 20 meters to 1000 meters, and look again at the wave number and frequency, and you can see the dramatic changes now in the structures, right? So this slope is getting larger here, so the wave phase speed and group velocity are changing with the equivalent depth, and all the waves, the family of waves, the mixed Rossby gravity waves, Kelvin wave, and the eastward and westward inertial gravity waves are very heavily dependent on h bar, which means even when you are looking for simplified solutions, eigenfrequency dependence on h bar means that you have to be really careful for in selecting h bar. That is a separate problem that we will look at later on. Okay, so just remember this constant basic state dispersion diagram. It's very easy to remember in terms of the basic families of waves: the Kelvin wave, mixed Rossby gravity wave, equatorial Rossby waves, and the eastward and westward inertial gravity waves, and the dependence on the equivalent depth. So we'll add the impact of changing background state later on, especially in terms of easterly and westerly as the most basic things to look at, and how they affect the wave number and frequency, and hence the width of the equatorial trapping. This we had already mentioned in terms of how Doppler shifting is affected by the background state, right? So we'll come back to these sorts of details. So really cute figure, really concise in terms of the amount of information that's contained in them. So even if you're not supremely comfortable with the equations and the derivation, that figure and interpreting that figure should be made intuitive by making sure that you understand it correctly.